Hi, this is John Bostanci talking about a general quantum duality for representations of groups with applications to quantum money, lightning, and fire, based on joint work with Barak Nehoran and Mark Zhandry. Before getting into our work, let me first set the scene. In 2023, Zhandry outlined a simple and elegant way to construct quantum money from abelian group actions. However, the fact that his construction only worked for abelian group actions meant that the security proof had to be done in the generic group model, and additional complications were needed to make the security work. The hope was that by generalizing this scheme to work for non-abelian groups, we might be able to get around many of these problems. However, at the time, it was not clear how to get the construction to work for non-abelian groups. This led us to an interesting algorithmic problem concerning the representation of groups. The first part of this talk will be devoted to this problem and the theorem that we call the general quantum duality theorem for representations of groups. Suppose that we have two orthogonal states, psi and phi, and we want to understand the complexity of mapping between psi and phi. In particular, we want to know how hard it is, or the computational difficulty of implementing a swap operation that maps both psi to phi and also phi to psi. It turns out, in the work of AAS, that this computational task of swapping between two orthogonal states is equivalent to a particular distinguishing task, namely the task of distinguishing between the plus and minus superposition of the two states. I will note that because the states are orthogonal, both these tasks are information theoretically possible. The key revelation of this theorem is that there's an efficient reduction between these two. Now suppose we have a collection of more than two states and a bunch of mappings, UG, between them. Is there some measurement type task that characterizes the complexity of implementing all of these mappings? It turns out the best way to characterize a collection of mappings is as a representation of a group. A representation of a group is a mapping between a group G and a vector and unitary matrices on a vector space V. The thing that makes it a representation is the fact that it respects the group structure. In particular, if I take the representation of G and multiply by the representation of H, I should get the representation of G times H, where G times H is the product in the group. Every group G has a dual group G hat and a collection of special representations, which we call irreducible representations, or irreps for short. The important thing to know about irreps is that for every representation R, you can write a decomposition of its vector space into a direct sum of W lambda I, such that the representations are all block diagonal in this decomposition. In particular, they simultaneously block diagonalize in a similar way that commuting unitaries simultaneously diagonalize with respect to a special basis. Suppose that we write psi lambda ij to be a basis for W lambda I. Then we could imagine doing a full measurement in this basis. In particular, this would correspond to a mapping that took psi lambda ij to a classical description lambda I and j. However, note that each copy of W lambda I is identical to every other copy, and the representation is block diagonal in this decomposition. So it'll be very difficult in general to extract or to measure information about the I register. Therefore, the next best thing is a computational task that we call Fourier extraction. We can think of this as a coherent measurement in the Fourier basis up to the ambiguity in the I register. So a Fourier extraction is a measurement that maps a superposition over psi lambda ij to some state phi lambda I that only depends on I, a classical description of lambda, and a superposition over j, where the superposition is the same superposition as you started with. We say that lambda has been measured and j has been extracted, and we call the remaining state, which only depends on I, an archetype state. Note that for two different I, these archetype states should still be orthogonal, although they might be we can think of them as being in a hidden random basis. Our main theorem is that you can efficiently implement a representation R if and only if you can efficiently implement Fourier extraction in the irreducible subspaces of R. Note that, again, both of these tasks are information theoretically possible, and our contribution is showing that there's an efficient reduction between the two, both ways. With this algorithmic task possible, let's now describe how we can build quantum lightning from non-abelian group actions. The no-cloning theorem is a well-known result in early quantum mechanics, and it states that there is no process that can clone an arbitrary quantum state, in particular if the state is not known to the process. Taking this idea, Stephen Wiesner in 1970 came up with a notion called quantum money, today known as private key quantum money. Private key quantum money is a family of states indexed by serial numbers S, such that a bank can efficiently create the states and verify them if they were taken back to the bank, but no adversary can take one copy of a quantum money state and produce two valid copies of the same money state. In 2007, Scott Aronson proposed a variant of quantum money that could be verified by anyone. Today we know this as public key quantum money. And we can go even further. In 2019, Mark Zhandry defined a collision-resistant variant of quantum money where not only can no efficient adversary produce two copies of a quantum money state given one, in fact, not even the bank itself can prepare two copies of a quantum money state with the same serial number. While all these properties are nice to have, constructing them has been extremely hard. There have been many failed and half-realized attempts at constructing quantum money, public key quantum money, and lightning. In the first column, we have schemes for which the security proof is only conjectured, or schemes that used to have security proofs but have since been broken. There have also been a number of works proving security of quantum money relative to certain oracles, usually quantum oracles, but not always. More recently, there's been a line of work constructing quantum money from group actions. Many of these papers require what's called the generic group model, which is also an idealized model of computation, but generally considered to be more realistic than a quantum oracle or other kinds of classical oracles. Finally, in 2019, the work of Zhandry showed that you could get quantum money security from post-quantum I/O, or indistinguishability obfuscation. However, post-quantum I/O is an extremely powerful cryptographic primitive, and we currently have no candidate constructions of it. So it really just passes the buck on to finding an even more powerful cryptographic primitive. In this work, we will describe a particular security assumption under which we get quantum money. And the security assumption doesn't require any idealized model or black box models. It'll be in the plain model. So I need to first tell you what a group action is. A group action is a pair. A group action is a kind of representation of a group that's described by a set X and a starting element and an operation star that takes a group element and a set element and gives us another set element. Like I said, it's going to be a representation of the group. So if I take G star H star X, I should get GH star X, where this is the product in the group. Finally, I will tell you about the quantum Fourier transform. Remember that when we were describing a measurement in the Fourier basis, we talked about an operation that mapped psi lambda ij to a classical description of lambda, I, and j. In general, we could call any transformation that performs this mapping a Fourier transform. However, if we look at a particular representation, namely the left regular representation, where u sub g maps h to g times h, then we get a Fourier transform that looks like this. We're summing over group elements and dual group elements lambda, I, and j. This is similar to the textbook definition you might see for the QFT for non-abelian groups. And indeed, if we look at an abelian group, I and j both only go up to 1, and we recover the roots of unity that appear in the standard textbook definition of the quantum Fourier transform for abelian groups. Now, let me describe our quantum lightning scheme from group actions. Let me first tell you how to mint a quantum money state. First, prepare a uniform superposition over group elements. Next, apply the group action controlled on the first register. Finally, apply a quantum Fourier transform and measure the first register to receive a serial number, lambda, and a quantum money state that's corresponding to that serial number. Now let me tell you how to verify a quantum money scheme given a serial number lambda and a copy of the quantum money state. The scheme will be very similar to the minting. First, prepare uniform superposition over group elements in another register. Then apply the group action controlled on the first register. We see this state L lambda kj. I'll write it this shorthand, but you can think of it as being a copy of the money state where the group element is stored in the clear instead of as G star X. Finally, apply QFT to the first register and measure lambda. To see that this scheme works when given a valid quantum money state, note that the verification and the mint are essentially the same algorithm, and applying a projective measurement to twice to the same state should give us the same result each time. So this verification, when we plug in a valid serial number and quantum money state, should give us exactly the same lambda, and we'll accept. Finally, let me next tell you about pre-action security, which is a security assumption that we will use to get quantum lightning security. Recall that the group action acts like this. If I take an element H and I act on a set element G star X, I should get another set element H G star X. Now let me define a pre-action. If I act by a pre-action on G star X, I will get G H inverse star X. Note that the inverse is just to make sure that it remains a group action. So if I apply another K to it, I would get G H inverse K inverse. So K going on the outside. I just moved it up here. So now we can define pre-action security. This will come in two parts. So the first part we call pre-action hardness, which states that it should be hard to implement a random pre-action. Namely, if I gave you a set element and a group element H, it should be hard to output G H inverse star X. The second part of pre-action security is what we call pre-action indistinguishability. This states that it should be hard to distinguish between a challenger that applies a random action and a challenger that applies both a random action and a random pre-action. So in reality, this describes an interactive game where an adversary first sends a quantum register to a challenger flips a coin, and then either just applies a random action to that register or chooses to apply both a random action and a pre-action to that register before sending it back to the adversary. Let me quickly tell you about how we get lightning security from pre-action security. So assume for the sake of contradiction that we have broken lightning security. In particular, we've managed to prepare two copies of the same money state. And for simplicity, let me assume that the register I of both the money states is also the same. We will be able to deal with this case, but for the purposes of explaining how things work, it'll be easiest if the I register is the same. Let's see how we can break pre-action security. First, just send one of the copies to the pre-action indistinguishability challenger. Remember, this challenger will flip a coin and either apply a random action or apply both a random action and pre-action. Second, just perform Fourier subspace extraction or Fourier extraction on both copies of the state. And third, do a swap test between the archetype states you get after performing Fourier extraction on both copies. The key insight is that performing a random action, because the action is block diagonal in the decomposition W lambda I, will not change the information stored in the I register. However, applying a random pre-action will essentially randomize the I index. So when we do the swap test, if the challenger has applied only a random action, our swap test will accept with probability 1. Whereas if they have applied a random pre-action as well, this should only accept with probably roughly a half. Our main theorem is the following. So given any group action that satisfies pre-action security, our quantum lightning scheme is secure. Finally, let me tell you about some possible instantiations of the quantum money scheme, or quantum lightning scheme. So the one that we feel is the most promising is from a group action that's implicit in the Michaelis cryptosystem. The Michaelis cryptosystem is a promising candidate for post-quantum cryptography. So here, our group is a symmetric group on n elements, and our matrices are n by m matrices, elements from some finite field. We should think of these as being code words of some error-correcting code over F. Now, a permutation acts on a set element by first permuting the columns and then row-reducing the matrices. It's a standard assumption in the Michaelis cryptosystem that performing a random permutation and then permuting and then row-reducing a particular starting matrix yields a matrix that is indistinguishable from the result of row-reducing a random matrix. So it's reasonable to assume, we think, that this group action satisfies pre-action security, although we have no proof. If it does satisfy pre-action security, then we believe this gives a promising avenue towards instantiating quantum lightning in the real world. Finally, let me leave you with some open questions. The first of which is, can we relate pre-action security to a standard assumption like discrete log? In particular, it's not hard to see that if the discrete log is easy, then pre-action security will also be easy. Namely, pre-action security implies discrete log hardness, but the other direction is not so clear. Secondly, can we build other interesting unclonable cryptography from pre-action secure group actions? For example, one-shot signatures or copy-protected software. And finally, the pre-action indistinguishability game is not an efficiently falsifiable assumption because we assume that it's hard to implement a pre-action and the challenger in the game needs to be able to implement a random pre-action. Is it possible to define an efficiently falsifiable variant of pre-action indistinguishability? For example, if we assume that there's some trapdoor that allows the challenger to implement a random pre-action, but does not allow the adversary to implement this pre-action. Thank you so much for listening.